am Brian Bodden. I'm very happy to be here. It's been 15 years since I was in this city, in this same facility, doing a conference. And today I'm going to talk about vector search in Spring with Redis. How many of you are doing things with vector databases? Okay, we have one vector database user. Okay, so hopefully you'll find out today that it's very easy to get started with vector databases, Similarity Search, and if you, for example, work in e-commerce or anything that has a visual aspect to it, that has images or catalogs of images, implementing visual search, it's very easy to do nowadays. So that's going to be one of the topics we're going to be covering today. So you can reach me via email, Twitter, and my GitHub account. It's open for you to grab as much stuff as you want. I am a Java champion. Apparently they let anybody in, so it's... And today's agenda will be first going to talk about the data balance. Why do we have this resurgence of vector databases now? Vector databases or vector support in databases actually has been around for a long time, but only a few vendors had it because there was not that big of a demand for it. And we'll talk about why that is and how things have changed over time. I'll talk a little bit about Redis in case you're not familiar with Redis. Actually, let me see a show of hands. How many of you have used Redis before? All right, so we can probably do a quick intro and not spend too much time there. Then we'll talk about vectors. So I actually been doing a master's in data science, and I've learned a lot over the last four and a half years. It's taken me a long time because I'm an old person. So, but the world of data science and machine learning and AI, it's so broad. There's so many topics. And right now, for example, the field of NLP, where LLMs come out of, it's moving at a pace that it's almost impossible to catch up. I started doing a lot of computer vision when I started my data science adventures. And every once in a while, I will check to see what was going on in the NLP world. And one day I just blinked and LLMs appear. So it's a very rapid, exponential curve. So we'll talk about embeddings and vectors, which are two very similar terms, but one is more conceptual and the other one is more practical. We'll talk about vectorizing, the art of turning unstructured data into vectors that you can do something with. Then we'll talk about Redis in Spring, because we're going to basically do Spring-based demos. And one of my goals is that you don't have to do Python only to do data science, or to do actually things that are productive and can improve your business. Spring and Java are still king in the e-commerce world and in the enterprise. So if you can get all the benefits of machine learning, LLMs, Gen AI into that world, that's a perfect marriage. Plus, you've probably seen the statistics about Python, how much power it consumes versus Java. So C, it's the greenest language. Then you have Rust. Then you have Java. And then on step or number 64, it's Python. So if you're doing Python with a lot of compute power, you might as well set the forest on fire. So. And then we'll talk about vector search, which is actually the big topic that everything comes together. So let's talk about vector similarity search. So this is the TLDR, too long, didn't read. Why? The majority of data that we get now, it's unstructured. That means that is click streams, documents, images. It's not data that comes neatly packaged in columns and rows. So we need to find a way to use that data. We need to be able to have a short time from when the data arrives to the time that we can actually use the data. And in the past, that time was a long time. So for example, if you had an image that arrived for a new product in a new e-commerce catalog from a vendor, if you wanted to put descriptions of that item that were not part of the text, then you would have to have somebody manually label or tag the images to say, for example, in this picture, there's a dress, and the dress, it's red, and it has a floral pattern, and the person is also wearing a shirt with a spaghetti strap shoulder arrangement. So those things were almost impossible to do with computers. You couldn't automate them. So you have to hire people to do this. You probably heard about the Amazon's Mechanical Turk. So the Mechanical Turk in history was basically what appeared to be like a robot, but it was actually a person inside doing all the work. And Amazon took that name too to mean a distributed system of computing where the compute nodes were humans. But we all know that that doesn't scale. So how do we deal with this? So vector databases, they excel at storing structured data, but not directly. You have to transform the structured data into a compressed, flattened format that you can manipulate. And how? There's a lot of vector databases out there now. Everybody, has a vector database now. We do too. We have had one for about 4 years now, 4 or 5 years. In Redis, an in-memory first database, that it's a key value database, where the value could be a lot of different things. One of those values could be vectors. And then we have a search engine that understands vectors. So you can do very fast searches on those vectors. I forgot I had little animations. So AI and ML in Java. Why would you want to do this? It's very easy to get started with Python. I feel that one of the reasons that the Java world didn't beat the Python world, we actually were the primary language in education for machine learning and AI. And then at some point, Python surpassed Java. And my theory is that it was the advantage that Jupyter Notebooks gave Python. Having a document place where people can experiment and rapid prototype things. So we lost that battle right there, but we can still catch up. So why Java? So Python is number 1 in terms of popularity, but Java is number 2. So yay, number 2. And there is a growing ecosystem of frameworks. There's DJL, which is a deep Java library. I've been using that one a lot. There's DL4J, which I haven't played much with. Weka, it's been around for decades. So this is one of those frameworks for machine learning and AI that's been around for, I think, 20 years. And then there's OpenNLP. And then now we have the new frameworks that work with LLMs and RAG systems. So for example, in the Python world, they have LangChain. In the Java world now, there's LangChain4j. There's also Spring AI, which is actually becoming really popular. It's fairly new, but it's moving pretty fast. And Microsoft has something called Semantic Kernel, which has .NET and Java versions now. And so now we know why Java, because it's still number 2 in the world, but in popularity. But in terms of usage in enterprises, we're still pretty much number 1. I think it's like Java and then .NET, and then everybody else. So Spring dominates the Java ecosystem. This article by Brian Vermeer says that 60% of the Java world uses Spring in one way or the other. So now let's talk about the root cause of why we have vector databases, which is a data balance. And it's all about structure versus unstructured data. Structured data, it's a data that we're super familiar with, rows and columns. And every column has a type. So you know what to expect from that. There's probably a format that only allows certain values to go into those columns. So everything is very rigid, and it has that same shape all across the relational world. We have a grid of values. Some of those values could be pointers to other places, foreign keys, but that is, it's a very flexible environment, but also if you take complex data and try to model it as relational data, sometimes it becomes unusable. In things like images, sounds, free-form text, it's impossible to model that way. In the old days, we used to have, we still have club and blob fields in relational databases. So what you did is you took an image and you put it into a blob, And all you could do is find the record by other values and then get the image out. Same thing with text. You will have a club, and you will basically put the text in there and just get it out. You couldn't say, search inside of this big text for this pattern. You have to pull all the text out, do that in memory, and then figure out if that row was a candidate for what you were looking for. So the balance of data has changed radically. 80% of the data that we generate now, it's unstructured. And this started with, like, for example, social media, reviews, e-commerce systems, where now you have not only the data generated by the system itself, new items being created, things being purchased, but now you have user reviews, you have user preferences, you have the ability to have, you have this explosion of data that it gives you a lot of advantages in terms of having a rich amount of data to do things. But if you can't react fast enough to those that data arriving, then it's not really useful. And this percentage is expected to grow, I think, at a 36.5 rate. So that 80%, probably it's 85 by now, because that is from 2020. So the way that I organize data in my mind, now it's like this. So you have in the bottom this triangle, in the size, the width of the triangle, the pyramid right there, implies how much data we have to deal with in organizations. So at the bottom we have structure. So schema, well-defined data, things that have been around for a long time. If you work in banking, insurance, hospitality, healthcare, there are databases that have been around for longer than we have been alive. And those are the type of databases that survive the applications and the change of time. But every time you want to build something against them, you're forced to basically deal with their structure. Then we have semi-structured data. And once we started basically doing a lot of document management, that semi-structured data exploded. A lot of companies, I've seen a lot of companies in the US that basically 90% of their businesses dealt with Excel spreadsheets, which scares me deeply. You see them like just in a SharePoint drive or a shared Google Drive, and it's like no version control. You know, somebody changes one formula somewhere and the whole company collapses. That really scares me. But that's the type of data that it's semi-structured, where you have spreadsheets, even XML and JSON, it's semi-structured because the contents can change. You might have a JSON schema or an XML schema to validate things, but that typically happens between B2B systems, nothing that it's human generated. And then you have quasi-structure, which is typically where we get into the world of streams and stream processing in large amounts of data, time series. And then at the top of this, we have completely unstructured data, which images, sound clips, full text documents like PDF files. That's the type of stuff that vectors are really good at dealing with. All right, so how do we deal with the unstructured data? So there's a few approaches. I mentioned before that labeling and tagging was the old school way to do that. And the act of label or tagging something at the higher level, it's called feature engineering. You're basically extracting features out of the data. And the engineering part depends on whether it's teaching a human how to recognize a pattern. So they can say, oh, these are what the floral dresses look like. These are what the striped dresses look like. These are what, you know, the paisley dresses look like. And a human will basically do that. But now we have machine learning, so we can train models to recognize patterns in a lot of different things like images, even sounds, and text. So we still do a little bit of manual tagging, but actually happens more for the training data that we feed to the models. So an example would be, imagine you have a bicycle here. And a bicycle has a set of features, like a frame color, a tire color, things of that sort. So a human will basically go and create the entries for each one of the elements in the catalog. But then things get more complicated when you have something like reviews. A review could be hard to discern whether it's a good review or a bad review. I normally do sarcastic reviews, and I try to be funny. So for a human to be able to pick that up, you have to read it carefully. If you just look like, this is great, it ruined my life. If you just read that this is great, then you're like, oh, it's a good review. Let's move on. With machine learning, you can now have, for example, sentiment analysis. So you can do keyword, matches on things, but you can also say, is this a positive or negative review? And then if it's a negative review, then you might actually do more analysis on those. So imagine we have some of those features. And in this case, I kind of made it numeric because it's easier to visualize that way. But imagine you have features that are star reviews. In our star reviews are for the bicycle ease of assembly. For some of those dimensions, and we're only going to use 3, obviously, because we can visualize things in 4 dimensions, but imagine that bicycle landing somewhere in this multi-dimensional space, in this case, a 3-dimensional space. And each one of the items in this space would have a value per dimension. So in this case, we would have the 4 for the ease of assembly, the 3 for chain quality, and the 1 for seat comfort. And that little set of values that looks like a Java array or a NumPy array, it's a vector. So in machine learning, in computer science, a vector, it's really just a list of floats. They do have orientation and magnitude, but obviously after 3 dimensions for humans, we don't really have a concept of how to visualize that. But the math still works. It works on 2 dimensions, 3 dimensions, and then n dimensions. And that is the factor that allows us to take something that is high dimensional data and deal with it like if it was a smaller dimensional system. So now that we have that little theory out of the way, I'll talk a little bit about Redis. So Redis is a remote dictionary server. So if you ever wonder what the word meant, or I always, before I started using Redis, I thought it was red is. And I'm like, I don't understand. So yes, it's a remote dictionary server. It's an in-memory first environment. That means that it's optimized for memory, but it's also optionally persistent. So the idea is that every operation, every algorithm, it's designed with memory efficiency and memory speed in mind, in dealing with all the advances in hardware. So in Redis, everything, it's a key. So it's a key value database. And the most common type of value is a string. And that's why Redis is really good as a cache, because you basically have a key and a value, and the value could be an HTML page, a JSON response, anything that you want to cache. And all you have to do is basically ask Redis, do you have this, before you hit another database maybe. So caching, everybody pretty familiar with. But Redis can store other data types like bitmaps, bit fields, hashes, lists, sets. So if you remember in uni, all the data structures from CS 101, we kind of have values for each one of those. And the idea of having data structures that are specific like that is that you don't have to change your object model to match the relational model or a document model. If you have something that is hash-like, you can store it in a hash in Redis. If you have something that's a list or a set, you can store it in Redis. And not only the storage is, to me, secondary. It's the operations you can do. So every data type has a set of operations, set of commands, and those commands are highly efficient to work on those data structures in memory inside of Redis. So there's also sorted sets. If you dealt with leaderboards, sorted sets is the typical structure to use for that. You also have geospatial indexes. You have probabilistic data structures like hyperlog, Bloom filters, where you can basically count very large number of things in linear time. So imagine that you had to do a select star to retrieve millions of records to check something, whether a value has been used or not. In Redis, with a Bloom filter, you can, for example, every time an email, you create a new account for a user, you basically register that email with a Bloom filter. And the blue filter turns that into a very compact representation that it fits in constant space. And you can also ask questions in constant time. So it doesn't matter how big your database gets, you can always, as long as you register that email or that unique thing with the filter ahead of time, you will basically always get a response back of, is that email taken? So there's also streams. If you've done things like Kafka, there's a streams type of data type. So there's a lot of flexibility in the backend. And time series. So if you're dealing with sensors of data or events from, for example, an e-commerce website, those can come in as timestamp payloads. And there's also JSON, which basically it's a super flexible document format. We probably all work with JSON every day of our lives now. It used to be XML, now it's JSON. So now let's talk about vectors. So how do we store and create those vectors? So first of all, what is a vector? We kind of talked about this. It's a numeric representation of something, anything, in n-dimensional space. They can represent anything. Documents, images, audio, video. If you have some kind of format and some kind of model that you can basically extract a representation of that, then you have a vector. And one of the nice things about vectors, that anybody familiar with, like, for example, convolutional neural networks for vision. So you know that those networks typically classify something, you know, like here's a cat, dog, or hot dog. Huh? The way that they do that, it's basically by extracting patterns. So like convolutions is kind of like a filter that basically moves through the image and extracts and compresses, and what you get then it's something that to humans doesn't look like anything, but it's the patterns, the essential patterns of different parts of the image in different aspects of the image. So each layer might pick something that looks like eyes or noses or mouths, and that's actually features. So those are features. So a convolutional neural network extracts features out of something like an image. But for vectors, we don't want the classification. We don't want to know whether it's a cat or a dog or anything like that. We just want the features. And we want the flattened, optimized version of those features. So imagine it's like zip or like gzip. You're basically taking something very rich and high dimensional, and you're compressing it and making it flat. So what we normally do is, on some point in that neural network, we grab one of the flat layers near the end, and those are your embeddings. So a lot of models that were used for classification, nobody basically was using them for embeddings. But at some point they said, oh, what if we grab the numbers on this layer and do something with them? And then they realized that, hey, all these things are comparable. You can compare them with different metrics. So that's where basically the power of machine learning and vectors comes together. So again, you can quantify features and characteristics of something, and they're comparable. So imagine these are word vectors. So there's an algorithm well-known called word2vec. And word2vec takes a word and maps it to a small vector. So for example, in this world of vectors, the word for queen and woman are at the same inclination angle association as king and man. So you get basically semantic groupings of things. So things that are similar are together. Things that act in a certain way might point in the same direction. This is an oversimplification, but with word2vec, you kind of see it that way. For example, the relationship between big and biggest and small and smallest, it's going to be kind of the same vector, but in a different portion of that space. So, yeah.
It is cutting the edge. To go back to the previous one.
Yeah.
The big and the biggest
Yep.
small and smallest, because it seems to be in the same direction. If you cut it down in a different dimension, they both can come together.
Exactly. Yes. Yeah. And one of the things that vectors sometimes have translational symmetry. So you can basically get, by having two vectors that are related in a certain way, you can then move them to find something related to one end of the vector, and then look at where that same endpoint is and find out the thing that it's equivalent to the relationship. So there's a lot of nice tricks that you can do with vectors. So here's a few other examples. King, queen, man, woman, walking, walked. Sometimes they're based on the model. So the model will determine what things your vectors convey. It could be language structure, like the tense of the verb. Or, for example, it could be something more coarse-grained, like countries and capitals. So it all depends on what you are encoding, what you're using to encode, and how it maps to that space. I really like this visualization because it kind of creates almost like a chromosome color scheme of different things. So you can see here that I have king, and for each of the values, so imagine each one of those squares, it's a value between -1 and 1. And what this this article did, is just colorize them. So he created a palette of colors that he could map different values. And here's king, there's man, and there's woman. And visually, you can kind of see that there's some similarities in different places. But I kind of think of this visualization as chromosomes, as a DNA sequence of sorts. And then we're going to come back to that image because you'll see we'll do some math with vectors, and you see how things turned out. So let's create some vectors. And for creating those vectors, I'm going to use DJL, which is the Deep Java Learning Framework. It's not very easy, it doesn't roll off your tongue, but So it is a Java framework for machine learning. You can build, train, deploy machine learning models and deep learning models. It's similar to something like PyTorch or TensorFlow, but it's in the Java world. And it also connects, so you can use models from PyTorch, from TensorFlow, directly from DJL. Spring AI uses DJL as one of its dependencies, so it can get access to things like PyTorch models and things of that sort. So if you don't want to go through an abstraction layer like Spring, and you have let's say a servlet application that needs to use a machine learning model, DJL would be a good choice. So you can use PyTorch, MXNet, which I think MXNet is kind of deprecated now, TensorFlow, and the Onyx format, which is a typical format for machine learning models. In the data science world, what has happened in the last few years, the last 5 or so years, is that now we have models everywhere. And eventually people started to think, hey, we need to organize this and put them somewhere, make them accessible to people. And also there's got to be a traceability of where the model came from, what data was used to train the model, what benchmarks we can apply to similar models so people can actually choose between the models. So we have model zoos out there, and it's better consolidated than before. So we have things like Hugging Face, where you basically can go in there and find, I need a vision model that can find, cats that look aggressive. You can basically look for very random models, and you will find them in there because there's a lot of people training models on very specific data. So now let's talk about similarity. So how do we find similar vectors? Oh, no, actually, we're supposed to do some experiments. I'm jumping the gun here. All right. So the first one I'm going to do, and hopefully you guys, is this big enough to see? Okay. So I'm going to explain what's going on in here. So this is a test, a very simple main method in a Java class. It's using DJL, so you can see the imports here. This one is using Deep Learning for J, which is another Java framework. And I use this one because it has that word vector serializer and word2vec, which is the algorithm that it's used very typically to show those word vectors. So the first thing I'm doing, it's loading the model. And you're probably all now familiar with like ChatGPT and all those models. So typically they basically mention how many parameters they have. So this one is a 6 billion parameter with 50 dimensions. And once I load that model, I can use this word2vec to create a serializer of sorts. And in here now, I'm going to create the word vectors for the words king, man, and woman. So you can see here that I'm passing the strings right here. But then I'm going to do some math with them. You can basically do things like king minus man plus woman. So what do we think that's going to result in based on the training data? Exactly. So let's run this just to see what it looks like. And it's not an error, it's that just because it's red. But see, here's what basically did. So I grab the top, I believe, 10 matches, and the top one, it's queen. So I did the math, and then I used that number that I got from doing the math, and I said, go find a vector that is the closest to this number. And the closest one was queen. So in Word2Vec, because it's a model that's trained on language, words have this relationship. In that relationship, it's encoded in the vectors, so you can extract it. And you can do fun things like math with them. All right, so that's one demo, one of the quickest ones. So let's talk about similarity. So now you can see that, for example, in this multidimensional space, you can compare things. And let's imagine that it's 2 dimensions for now, or 3 dimensions. There's a similarity metric called cosine similarity. And the idea is that for that one, you ignore the magnitude of the vectors, but you care only about the angle between them. So cosine similarity is actually really good for image similarity and sentence similarity. So if the angle is close to 0, that means that they're very similar vectors. Obviously, the closer 2 vectors are. But cosine similarity doesn't care if one vector is super long and the other one is super short. For that, you have to use other metrics. And there will be some models where that matters. So you have to pick the similarity metric that matches the environment and the training data that you're dealing with. So if the angles are close to 90 degrees, they're orthogonal. And depending on the model and the domain, that might mean something or something else. So for example, opposite vectors, what is an opposite word? An antonym? Black, white? But no, but black and white are colors, so they have a relationship there. So what is similar and what is different, it's very subjective and specific to the model you're dealing with. And of course, the models could be higher level things. So for example, here's an example of movies being mapped to a 4 dimension of whether they're good for children, they're artsy art movies, they're blockbuster like Marvel movies, or they're adult movies. I don't know what adult means in this context, but I believe it's just drama and serious movies, not the other adult movies. So what we saw before with that Java example, it's basically this representation. King minus man plus woman equals, kind of equals queen. And you can see now by the colors that you can kind of see that happening in there. And obviously this is the simplest example with one of the simplest ways to do embeddings that cares only about specific words. When you do this with sentences, there's models that basically do sentence embedding, then it will be much more complex to visualize. And here's another example that came from the Word2Vec paper, where you can see how things are kind of related in this space. And obviously what they did in here, it's they did dimensionality reduction to flatten the space into a 2D representation that would be somewhat helpful. But not always does it help to create a visualization. Sometimes you end up visualizing something and it means nothing to nobody. So you have to sometimes trust just that the values are making sense, which is one of the hard things with machine learning and using AI. You're adding a subjective piece of software that sometimes is non-deterministic, that has performance characteristics that are variable. So it's an interesting world. So there's a bunch of different distance metrics: Euclidean, Manhattan, Minkowski, Chebyshev, cosine, which is the most popular nowadays, and Hamming distance. You can, for simple models, you can do things like Liebenstein distance between words. So now that we know that, how do we get those embeddings out of things? Machine learning, obviously. Machine learning models now outperform humans in most tasks when it comes to vision. So for example, to having detection of objects in an image, now computer vision models beat humans. That's why I think that eventually we should not drive anymore, and we should let all the cars drive by themselves. As long as they're not humans in the equation, they will do the right thing. And as long as the cars can talk to each other too, yeah, we'll just sit on the back and have a martini and just get to wherever you need to go. So computer vision models excel at object detection and classification, and LLMs nowadays, have created an exponential explosion of usage in terms of their capabilities to deal with language. Don't be scared. So we talk about feature engineering, and this is just a very simple image of what it used to happen in the past too. Sometimes we had to one-hot encode things to be able to train a neural network to recognize the patterns. But the initial input data had to be something that was quantifiable, sometimes by humans. And that's no longer the case. So one of the nice things about machine learning models is that they capture the gray areas between something. So imagine you're trying to classify something as a shirt or a jacket. If you go from left to right, you can see that this is obviously a shirt. That's obviously a button shirt. That's a jacket or a shirt, I don't know. And that one, it's too thick to be a shirt. But he's wearing a shirt underneath, so that one's a shirt, the other one's a jacket, and that one's, definitely a jacket. So you can see how just in a very simple environment with only 5 elements, it's hard for humans to decide whether it's something or other. And with machine learning models, you have just a gradient. And that gradient can pick the right things as long as you say, I want things between this value and this value. And you don't have to go into this level of specificity. So machine learning models extract latent features that some of them might be obvious to humans, some of them might be completely invisible to humans. If you, going back to that CNN analogy where you see the convolution network extracting different things, different type of images, some of them we recognize. We're like, oh, that's eyes. This is noses. This is chins. But then you start seeing things like this is a monstrosity. I don't know what it is, but they're patterns. And that's why, for example, facial recognition, it's so powerful with machine learning. So the process of generating the embeddings, it's typically called vectorization. So taking something and turning it into a vector. So let's talk about vectorization. The recipe is fairly simple. Choose an embedding method. That means for the type of data that you have, pick the right machine learning model that would basically create embeddings. And the criteria depends on how fast can you create the embeddings, depending on your environment, how big the embeddings are. Sometimes you might get a model that has 7 billion parameters and 1,000 dimensions for your vectors. And you might get similar or sometimes even better results with a smaller model. So size does not always matter when it comes to machine learning models. It's mostly how the models were trained, how the data was curated to. So it's a lot of principles behind choosing one. So choose an embedding model, clean and pre-processed. So for example, for the demo we're going to do today, which is a vision demo, you have to kind of resize the images to the size that the model it's good at detecting. So if you pass one phase at a 32 by 32 image and one at 128 by 128, it's not going to be really good at picking them up, even though they're the same phase. But if you scale them correctly, you'll find out that they work really well. And again, it really depends on the model. So you can train the model too, but training your own models, it's something that typically nobody does anymore. We basically use models off the shelf, or we do fine tuning on those models so we can provide our own data to, let's say you have a model that classifies objects, yet you want now 5 more classes that can be classified. All right, so again, the 3 options: use a pre-trained model, that's the #1 choice out there. Fine tune, this will happen after you implement your solution and take metrics and measurements and figure out whether you need to basically have a better model. Because sometimes the problem is not the model, it's the data coming in, the pre-processing of the data. There's a lot of things that are going to play. And then the third one, it's custom training your own models with your own data. And for that, you have to have probably a lot of compute power and a lot of data. In most companies, sometimes have one or the other, but not both. So in a vector similarity, again, like that cosine similarity, it's the downline tool that we use to analyze the embeddings that were created. So I mentioned that there is model SUS. So there's things like TensorFlow Hub, there's Hugging Face, there's PyTorch Hub, and now every company that creates an LLM has their own model directory. So it's there's a lot of places where you need to basically go and find, or go and look to see if there's a model that meets your needs. Today we're going to use sentence embeddings from the SBIRD website. In this one, you can see how the model SU idea works. You have a model name. Most of them will tell you, how many parameters, in how big the embeddings are. But you can also see that now people are profiling those and creating test cases to basically do a performance analysis of all the different models. And I mentioned before that, in a normal convolution network, those last layers, the flat layers, is where you get your embeddings from. All right, so I'm going to talk about Redis OwnSpring, and I'm going to go through this fairly quickly. So Redis OwnSpring, it's the framework that we wrote for Spring that extends Spring Data Redis. And what it adds, it's all the things that Redis provides as extras now. In Vector, the vector database capability, it's one of those.
So Redis OwnSpring is an open source, right?
Huh?
Redis OwnSpring, it's an open source, right?
Yes, yeah. It's a MIT license, the framework. And we have versions of this OM framework for .NET, Node, Python, and obviously Spring. So I'm the maintainer of the Spring version, and they're all not equal in parity and features because the languages and environments are so different. But we try to keep them all in par. So Redis OwnSpring extends Spring Data Redis and uses the Redis driver under the covers, which is the most popular Java driver for Redis. So an example of how we map Java objects to Redis data structures, it's something like this. You have an annotation called Redis hash that comes from Spring Data Redis. You will have something like an ID, and then that object, when you store it in Redis, will kind of look like this. This one happens to be a hash. You have the ID, you have the name, you have the class that basically maps to the object. And it's a very simple mapping back and forth. There's also JSON. So JSON can accommodate deeper structures, obviously. And in here, you can see, again, the same thing. You have a film object, has an ID here. And you can see the film ID would match the value that's in the ID. In title, description, release year, all those things, you can basically deal with it. If you work with MongoDB, for example, this would be very similar. So there's repositories, just like there's repositories in Spring Data projects. There's two repositories for hashes and for documents. And anybody familiar with Spring repositories? Okay. So I'm not going to spend too much time in there, but you have a bunch of methods available to you that come out of the box. And also you can declare your own methods by basically using specific patterns to decide, what do you want to search for in your data. And what we do is we turn that into the query language for Redis automatically. So you don't have to learn the query language. You just have to, if you know how to use Spring Data, in many of the other projects, it's the same thing. So now let's talk about searching. So what we're going to do today is demos for searching. So there is a growing expectation for search to be better. Search interfaces used to be fairly simple, and now with machine learning Everybody that has an e-commerce, for example, site, if they don't provide visual search, you know that they're falling behind the times. So typical examples of visual search would be something where you can find, for example, some things based on specific data, but also an image. In a lot of mobile applications now for places like the Home Depot or Lowe's or IKEA, you can take your phone, take a picture of something, and it will tell you, whether it's in stock or not, or find me similar items to that. So when you see the similar items, that's typically a vector database somewhere doing some similarity comparison. And recommendations too. So once you have these vectors and users buy different things with vectors, you can create from that collection of things that they bought, those vectors, you can create a vector that represents the user behavior. And now if you find another user that has a similar vector in that space, you can see then what has user A purchased that user B hasn't, and then recommend those things to user B. All right, so let's talk about vector search in Redis. And we have three distance metrics, Euclidean, internal product, and cosine. Two indexing methods, HNSW and flat. The difference is one, it's more efficient. The other one, it's more precise. So depending on what you're doing, you might want to pick one or the other. And you can pre-filter the vector searches. So vector searches are k-nearest neighbors searches. And so they're expensive computationally. So typically, people will pre-filter based on other things. Like we saw that search interface where there's a color picker, where you can say, I want an item of this color. So you can say, I'm going to filter the collection, the whole collection of things by only the things that are that color, and then do vector similarity on that to make it more efficient. So in general, you want to basically find, based on the type of data that you have, the right model, so you can create vectors that can go into the vector database. And again, I think a lot of the speakers mentioned this, that we're talking about vectors. When you want to find something, then that input item, that input query, also has to be turned into a vector. So you can put it in the same environment and find where in that space they land. So again, this is typically what happens. You have your data using a machine learning model. You get embeddings. They get now stored in the database. They have some sort of metadata attached to them. And from that, you create indexes. And those search indexes are like traditional search indexes in something like Lucene, for example. But they also have the capabilities to deal with vector data. So as data is coming in, you have an indexer that updates and maintains the index. And then you have, on the query side of things, you have to, again, do the same thing. Convert things to vectors, pass that vector to a query engine, and the query engine will find in that space where that vector lands. And then from that point, you can go around and figure out the nearest neighbors for that. All right, so now let's look at the Celerity Match demo. We're doing too well, I'm good. So this demo, it's about facial recognition. And let me show you first. There's two parts to the demo. First, given a picture, find the most prominent face in the picture. And once you have that, then crop it and size it to the right size that works with the facial recognition model to do the recognition. So first, I'm going to show you how to extract faces. And let's look at the code here. So that would be, so this retina face detection. And here's that image that you saw on the slide. So this, at some point, this was the largest selfie in the world. I don't know if it still is. And what I'm going to do is this retina face detection. It's using the DJL framework that I mentioned before. And somewhere in here, I'm picking up that image, that largest selfie. And I am going to load a model called Retina Face that comes from PyTorch. So in here, I'm using a PyTorch, so a Python native model in Java, just like nothing else, like it was a jar file. In here, notice that there's a submodel. So what I can do is, sometimes given the data, you can ask the framework, find the best suitable model to do this specific task. But once I have my model in place, I'm going to have a predictor. In that predictor, then I can pass an image to predict whether there are faces in there or not. And then I'm going to actually draw bounding boxes around the faces. So let's go ahead and run this. And I don't believe I require Wi-Fi, but it's, yeah, so it downloaded the PyTorch model, and you can see that detected a bunch of faces. Each one of those lines, it's detected a class object of type face with certain amount of probability. So how sure is the model that this is a face? And you can see that most of them are in the high 90%. In the bounds, it's where in the larger image that face lands. So now let me show you where I found, so I basically found all the detections, drew bounding boxes on the original image, and I saved a copy of it. And that should be now under my output. So if I open that one, and I expand it, you can see here all the faces that were detected by the system. You can see that it starts failing when it gets very small at the top. But for the demo that we have, let me actually start it too, now that we are ready to be there. So here, so I'm going to first go to Docker, and this is my, let me extend this so I can see what the name of the, yes. So this is the VSS Celebs. So I have a version of Redis there where I preloaded the celebrity face vectors. So I'm going to go ahead and run that. And in my celebrity application, let me show you the domain quickly. So there's a celebrity object. In the celebrity object, it's very simple. I'm storing them as hashes. This came from a CSV file from a machine learning data set. And I have an ID, I have a name for the celebrity. There's a popularity ranking that came with the data set. And then I have two magic annotations that the Redis own framework provides. The first one, it's vectorize. Let me move that. Yeah. The first one is vectorize, which basically says, find the image resource that's being pointed by this string and vectorize it using the embedding type face. So it's going to use the facial recognition detection model. And the vector that gets created, put it in the image embedding field, which is down here. In that image embedding field, it's a byte array. So that's our binary data in Java representing the vector. And I'm going to also index that into the database. So now all those faces are going to be indexed. So I'll be able to search, if I given an input face, find a similar face. And you can see here in the controller, once they give me an image, an upload of the image, I can actually do a search with Redis own Spring after vectorizing the input image, extracting the face first, vectorizing it, I can do a search for similar faces. So let's just run this. So this is a traditional, plain vanilla Spring application. And all right, so you can see there that it's there's 11,637 celebrities loaded. Let's go to the browser. If I go to the browser, refresh this, I can choose an image. And in here, I'm going to pick, this sometimes is embarrassing, but let's pick, I'm going to pick a picture of my wife because she's beautiful, so it always works well. When I pick my picture, I'm like, I didn't think I looked like that person, but so I'm going to load that picture, and now I'm going to upload it. And you can see how fast it can do the image recognition. And notice my wife, it's a blonde American woman. And these are not blonde American women, but what you can see is that there's facial structure things, eye shape, nose shape things that humans are not really great at picking up. But this specific model picks those things. So it's And what I noticed in this one is that they did train it, some facial recognition systems ignore the hair. This one does. So if you have a very specific hairstyle, this system will basically be like, oh, you look like this person, even though the face might not be the same. So again, it all depends on what model you're using. So for example, if I pick here a picture of, let's see, Harrison Ford, and I upload that, you can see that it picked people that have similar facial structure. Clark Gregg went to the same college that I did and plays the same sport. He's just 5 years older. But again, that's, and notice in here, I have this 92.78 number. That is how similar that face, given the model, thinks is to the input face. All right, so how are we doing on time? Good? Okay. Oh, perfect, perfect. All right, so now let me go back to the slides for a second. And what I'll do is I'll stop this demo because I want to run another one. And let's stop that Docker image. And I'll start the next one. Okay. So back to the slides just for a few minutes. So again, we saw how facial detection works and how a facial recognition model can be used to deal with unstructured data. So I mapped that celebrity to the hashes. We have the index and vectorize, and then we use the entity streams in Redis OM to do a query to find similar faces. And obviously all the code, it's available so you can actually play with all this and see how it works. And again, the magic recipe was the two annotations that I show you, vectorize and index. You vectorize something, put it in another field in your object, and then index that object in the search engine in the database. So we saw the celebrity match demo. And now we're going to look at the fashion product finder. And this one's different. It uses text and images to basically find similar items. So let me go ahead and get this one running so you can see what it's all about. So this is, and this is actually, I embedded this demo as part of the project in GitHub. So if you download the Redis OM framework, you'll basically get the this demo. So I'm going to run the demo. You see, I probably have to start. Oh, I did start the. Let me see, Docker. Yeah, Docker's running. Okay. So I'm going to, let's see, did it start correctly? Yeah, so you can see here that there's about 2,800 products available. So if I refresh this, you can see this is what the fashion product finder looks like. And you can see that for each item, there is a view similar by text or by image. So let's apply some filters in here first. So this is the pre-filtering that I mentioned that you can do before you do a vector search. So let's say I'm going to find things for men that are footwear. I'm going to close that and reload this. So you can see I have a bunch of shoes in here. So now let's find shoes that look similar to this one by image. So you can see now that obviously the first one that we picked itself, it's the 100% match. But then you have a 96.8% match, which is that Vans in there. So you can see that the image similarity works fairly well with products, but this is not a model that was trained specifically on fashion items. It was trained on just images. So if I, for example, now do something by text, you can see now that things vary because we're looking at the description of the item and the name of the item. So it's using two text fields to do that. And in here, I can go again by image. If I apply filters and I remove the filters, I think I can just do this. Now, if I pick one of these and I do by image, you can see that all those goofy models are doing kind of the same pose. So my guess it's that the model also has a little bit of a pose estimation built in. So you can see, the type of things that you get. But similar, they're mostly men in here. They're all very similar looking. Their shirts are similar looking, and the poses are similar looking. So I don't know to what degree each one of those elements goes into the similarity. That's where you need to know how the model was trained and what type of data was used to actually train the model. All right. Now let me close up here. So the tools and techniques to unlock the value on structured data are available everywhere. Redis just happens to be one of the choices in there. If you want a lot of performance, that's what we are good at. And there's frameworks. So if you're a Spring developer, for example, you can use Redis on Spring and keep your Java code as Java code. You don't have to go and do Python to basically take advantage of machine learning. So you can take all of your unstructured data and put it in Redis, and we'll be happy to help you with that. Here are the links, but I would put everything too on GitHub on Twitter. So if you want to take a picture now, go for it. And thank you.